Black holes are astronomical events that are formed through gravitational collapses of supermassive stars. Black hole consists of a singularity at its center. It is the point where general relativity doesn't work, and there are various theories to define how the particular situation goes on in there. Black hole is often identified with a circular pattern around a black background. This background is called the shadow of black hole, and the circular pattern is called the photon sphere, which is formed by the light rays that fail to escape from the black hole, but don't really fall into it either. Any object that falls into the black hole forever continues its motion in the future timeline, leading to the singularity. Whatever goes into a black hole continues to remain there, or gets crushed at singularity, thus the entropy of the universe gets reduced. But according to the second law of thermodynamics, the entropy of the universe always increases. How is this possible? Are black holes completely black? Or in the terms of popular scientific notation, do they have some hair? Let's understand in this video. My name is Kyle, and you are watching The World of Science. A black hole is characterized only through its mass, its angular momentum, and net charges upon it. Other than these three, no single information can be obtained from a black hole. That is why scientists say that black holes have no hair. The 1970s was the era of young Stephen Hawking unlocking many mysteries, such as relating the singularity of black hole with the singularity present at the time of the Big Bang. Along with Roger Penrose, he worked on the mechanics of black hole. When light rays come toward the black hole, they will either be sucked up by it, or be established in a well-suitable orbit around the black hole. Thus, the path of light rays on the event horizon of the black hole must always be parallel to each other, or going away from the center of black hole. If the path of light rays would be converging, they will eventually fall into the black hole. So either the area of the event horizon always remains the same, or must increase with time, as the light rays keep revolving in the orbit around it. A black hole is a monster, devouring another star coming in the vicinity of it. Each time black hole swallows up another star, its area increases, represented by the growing radius of photon sphere around the event horizon. Jacob Bekenstein, the father of black hole thermodynamics, showed the similarity between increasing area of the black hole and increasing entropy, according to the second law of thermodynamics. He postulated that the event horizon of the black hole was the measurement of the entropy of the black hole. More the area of the black hole, the more will be the entropy. Any matter falling into the black hole increases the area of the event horizon, thus increasing the entropy. Hence, entropy outside the black hole will certainly diminish, but overall entropy of the universe will increase subsequently. Second law of thermodynamics shows that entropy is a function of temperature. Entropy is inversely proportional to the temperature, but this relation must imply that for black holes to have entropy, they must possess temperature. Up to that time, black holes were considered to be the coolest objects in the universe. Massive black holes have temperatures lower than the temperature of the cosmic microwave background of the universe. And if black holes have temperature, then as a black body, it must emit radiation in some form. Stephen Hawking proposed a mechanism that shows that black holes do emit radiation, just like any black body, and that depends upon the mass of the black hole. Bigger the mass of the black hole, lower will be the temperature, and thus slower it will emit radiation. A smaller black hole will have more temperature, and thus emit radiation at greater speed to achieve equilibrium. This radiation was named after Stephen Hawking as the Hawking's radiation. Based on all these studies, the properties of black holes have been classified into 4 laws, called the laws of black hole thermodynamics. They are as follows. Zeroth law. The zeroth law of black hole thermodynamics states that the event horizon of a black hole will always have a constant surface gravity all over it if the black hole is stationary. Surface gravity is the value of gravitational acceleration experienced at the equator, near the surface of the heavenly body. First law. The total change in the energy of the black hole is determined by the change in the surface area of the event horizon, change in the angular momentum, and change in electrical charge. These three properties, as we have discussed, are the only three hairs of the black hole. Second law. This law is similar to the second law of thermodynamics, and it states that the area of the event horizon will always be an increasing function with respect to time. Thus, the event horizon will always increase. Third law. This can be called the impossibility condition of the black holes, and it concludes that no black holes can be formed, with the parameter of surface gravity vanishing and approaching a null value. This is similar to the third law of thermodynamics, that says entropy of any state cannot approach absolute zero value. In 1974, Stephen Hawking made the seminal discovery that black holes emit thermal radiation. Previous to that, black holes were believed to be inert, and as the final stages of a dying heavy star. Recently, scientists from the University of Sussex have shown that black holes are in fact even more complex thermodynamic systems, with not only a temperature, but also a pressure. Scientists were completely puzzled by an extra figure that was appearing in equations, that they were running on quantum gravitational corrections to the entropy of a black hole. During a discussion on this shocking result on Christmas Day 2020, a realization began that what they were seeing was behaving like pressure. Following further calculations, they confirmed that black holes exert mysterious quantum pressure on their environment. So, black holes, one of the most complex objects in the universe, do have certain arrangements through which we can understand them better and make predictions about them regarding their origin and fate. What are your thoughts about black holes? Let us know in the comments. If you found this video interesting, please leave a thumbs up and share it with your friends. Do follow us on Instagram for daily quality content that'll make you fall in love with science. Comment down the topics that you want us to cover in our next videos. Do check out other videos on our channel. Make sure you subscribe to the World of Science. Until next time, stay scientific.